Welcome to Study Loop.
All right, so the first part asks for uh, part A wants to know wants to know the EMF induced in the coil when it is all inside the field, and so the EMF induced in the coil is by Faraday's law the rate of change of magnetic flux, and so magnetic flux, if you remember, is the number of turns in the coil times magnetic field strength times area times cosine phi, which phi in this case is 0, so this term is not 0. And area is the area of the coil. And so for part A and part C, you have the same answer, which is that EMF induced is 0. This is because phi is not changing, and that's because look at this: the number of turns of coil is not changing. Magnetic field strength is of course not changing when you're all in or all out, and area of the coil is not changing either. So nothing's changing in phi. Phi is not changing, ergo EMF induced is 0. Part B, however, when the coil is partially inside the field and partially outside, we're gonna say that x is equal to the length of the coil that's in the field, and the height is 0.4 meters or 40 centimeters. So area is 0.4 meters times x, or 0.4 x meters squared. Therefore, EMF induced is d phi dt. So this is number of turns is 1, so it's d dt times b times a. And so moving on to the next page, so so you pull out the b and you have d dt times 0.4 times x. We're not going to worry about the units just yet in here. So 0.4 is a constant that's pulled out here too. So you have 0.4, it's going to write down meters times b times d dt of x. dx dt, if you'll remember from kinematic equations, is just v, the velocity. So what we have here is 0.4 meters times b, which is in Tesla, and times v, which is the speed of the coil. And so this is 0.4 meters times 1.25 Tesla times 0.02 meters per second, or 2 centimeters per second for the speed, giving us 0.0100 volts for the EMF induced.